if we start with the LH packet first, let's just go through the answers here. So the first one we had on LH was what number?
1.
Number 1. Okay, number 1 was
36.
36. So this was just area between curves. Now up on the board here, we've got the stuff we've learned so far, the new stuff in chapter 7. Of course, we're continually just kind of flip-flopping here between adding in new stuff, but also going back and reviewing old stuff as we do, as we get ready for our finals and that kind of thing. So right now, the new stuff, we'll have one more quiz over new stuff. And then we'll have our 4 finals. And then we'll have, so that'll be like 4 quiz grades. Those will each be a 30-point quiz grade. I think when I actually put it in, I'll put the multiple choice will be 2 30-point quiz grades, and then the free response, I think I combine those into one 60-point grade. But essentially the same thing. So I have this quiz on this new stuff. Well, the 4 there, so that'll be like 5 quiz grades. Then we'll have that group paper we talked about at the end. We'll be working on. We'll have that group assignment that you can work on. And there'll probably be a homework grade in there as I've been coming around. And then the packets, those review packets that we do, I'll probably do a packet grade in there as well. So, but a lot of those grades won't come until a few weeks down the line, and as we get to the last 2-3 weeks, we'll have a lot of grades right above. So anyway, the new stuff we've done here that will be on our quiz will be the area between curves, top minus bottom, right minus left, if it's horizontal strips or vertical strips, okay? So we did that a couple days last week. And that's the LH packet. And then we had this new thing on Friday, which is length of a curve. And it's basically this formula right here. So if you're going to do the length of the F curve from A to B, you plug it into this formula. So you do the derivative of F prime, put it into there and go. So we'll get to that in a minute. So the LH, so number 1 was 36. What was next? 5 was 3 halves. Number 6? 1 half. Then what? 12 was 4 fifths. 15 was 2. 21 was 9 halves.
Oh. Yeah, I don't know.
We need to look at that one?
Yeah.
And then what else?
23.
23 is 6. Okay? All right. So on, if we take a look at 20... Which one was it? 21 you said?
Yeah.
Okay, if we take a look at 21 here, you got x equals y squared is basically what that's telling you. So you got x equals y squared, which is a sideways parabola. We've run into that a few times already, so hopefully you're okay. Now if you needed to graph that on your calculator, you would graph it as y equals plus or minus square root of x. You need the plus and the minus, so the top half and the bottom half. Okay, the top half of this is just square root of x. Bottom half is negative square root. Okay, and then this would be x equals y plus 2, which means that'd be y equals x minus 2. So it would be a y-intercept down here of negative 2, and it would come up here and it would come through like so. So where does it intersect? Well, I think it intersects at 1, negative 1 down here, right? And then it intersects up here at 4, 2. All right? So this could best be done with horizontal strips. Otherwise, you'd have to split it into 2 parts. So right x-coordinate would be the line. Well, the right x-coordinate would be this line, y plus 2, minus the left x-coordinate, which is the parabola. The left x-coordinate is y squared, dy, and the strips fill the space from where to where? Negative 1 to 2. So the strips fill the space from negative 1 to 2. So that would be your integral. So right x-coordinate is the line. Left x-coordinate's the parabola. Make sure you have x equals, so it's your x-coordinates you're looking at. Right x minus left x. Strips fill the space from negative 1 up to And that was supposed to be 9/2. Is that the one that was 9/2? Okay. So that's area between curves. Now I did want to make one comment about number 5, and just to remind you of the difference between area between curves and area under a curve. So on number 5, you have this cubic right here, they called f. If I just did the integral of f from, in this case, -1 to 1, if I just did this integral, it's hard to see what the shaded area was, but it would be this red area. What's that area? 0. That's 0, because you got some positive, you got some negative. But we said that when you do area between two curves, and notice how they told you the curve. They gave them to you as f equals this and g equals this. Well, that means g equals 0 is the x-axis. So we want the area between that curve and the cubic curve. Well, that means we want top minus bottom, which makes what happen? Positive. And over here we want top minus bottom. So, which makes it positive. So we were looking for a positive area. So that's why you did not want 0 on number 5. So top minus bottom here would be f. You go from -1 to 0, and you'd have f minus 0 as your function. And then the second one would go from 0 to 1, and it'd be 0 minus f. Top minus bottom. Now you do know there's symmetry there. So you could just do 1 and double it. You could do that too. When you see a function like this, you know what its graph looks like, so you know something's negative. You can do absolute value bars to get that total. Because it's kind of like net distance versus total distance, isn't it? Which is something we're going to talk about a little more again today. But it's kind of that same thing. But understand that area between curves is that idea. So one way is the absolute value bars do it. Another way is to split it up. Now, we're going to talk about that exact thing today on a problem where we're going to talk about net distance and total distance traveled, and splitting it up like this is kind of where you look at the stopping points. Remember we talked, it's hard telling with all these breaks, but it wasn't that many class days ago, who knows how many actual days it was, but where we talked about, you know, if a particle's moving back and forth, and you want to know the total distance traveled, you got to find when it stopped and turned around. Well, that's kind of what this point is right here. It's kind of a turnaround point, right? If you think of this as a velocity graph, the velocity's positive till there, then negative there, well, that means it was going this way, and then it turned and went this way. And so splitting it up at its turnaround point is kind of how you can do total distance traveled. So hopefully you can see a connection there between how we're doing this area between curves and how it's that same thing when we do use these integrals to get distance from velocity and set up integrals doing that. Okay? All right, so just important kind of idea there. All right, let's switch to the length of the curve stuff. So let's go to the book problems. And what was the first one we did on that? That was number 6. Now, number 6, you were supposed to do a 20 midpoints. And so what I said, for those of you that weren't here, is you first have to set up the integral. Now, on number 6, they said you want the length of the curve. So some of you that were gone had a few questions about this. So let's just make a comment about this. You've got y equals 1 plus x squared, which would just be a simple parabola shifted up 1. Okay, it's just this. We're supposed to look at the length of the curve from 0 to 1. So what they want is just this length right here. The length of that piece of curve. That's what they're looking for. Well, here's the formula of how you do it. So this is our f function right here. So we set up the integral from 0 to 1, square root 1 plus, what goes here? F prime would be 2x, and then we want to square that. So 2x squared would be 4x squared. So we would go ahead and do that, and we would set that up. Now, in part A, they wanted you to approximate the length of the curve with 20 midpoints. Well, that's where you get out that area document that I sent you, because anytime it's 10 or more, you get to use that area document. So once you've set up your integral that you're trying to find, then you go to that area document and do the RAM. That's probably the easy one to do, run the RAM program, and put that integral in there, and you can get your M20. What did you get for the answer on that? It was 1.479. Okay? In part B, it says find it exactly. That said use a table of integrals. We said just use your calculator. And sure enough, it's like 1.4789, something, something. Okay? So that's 6. We'll skip 9 for a minute. Let's go to, what was next? 12. Okay? Now, the other class, we'll see how you guys did. The other class didn't do so well on this one. They give you this integral on number 12. The integral from 0 to 1, square root 1 plus x dx, right? And what's the first thing they ask you to do? Just do it. Find it. Find the answer. What do they say on number 12?
They said first calculate I exactly.
Okay. Now it said by anti-differentiation, right? So technically, that would be like a no calculator. You should go ahead and do it. I'm not that concerned with it right now, okay? But that would certainly be something we'd want to be able to do. You could do a u substitution with the inside, the 1 plus x. Of course, the du just be dx, so it'd be a pretty simple one. But you know, that's something we should be able to do, okay? But for right now, let's just say you typed it in your calculator. What do you get?
1.21895.
Okay, so we'll round it to 1.219. So that's what that is, okay? So that's part A. Part B says, this can be thought of as the area under a curve. What curve? And draw a sketch. Okay? So what would be the curve that this would be the area under? Yeah, very easy. It's simply that function right there. And this is the area under that from 0 to 1. So we draw a sketch of that, and this would be the square root graph, just shifted 1 back to the left. So this would be that picture right here, from 0 to 1. It would just be this piece of area right here. So that piece of area right there is 1.219. Right? That's the area from 0 to 1 under this curve. Okay, well, that's how we learned what integrals were, right? When we first learned about integrals. It was an area. It was the area under this curve. Okay, and it's a square root shifted 1 left. So there it would be. Okay, then part C says what? It can also be thought of as the length of a curve. This new thing we learned. Which curve? And then I'll ask you to draw a sketch. Find a function f that this could be the length of the curve. So we got to find what curve we'd be talking about.
This is x to the 2/3 x to 3/2.
Okay, you got to keep going because, all right, so let's back up. You're partially right. We got to get that, and Ryan's got it, 2/3 x and 3/2. Now, first of all, we got to remember our formula. Our formula, which is up on the board here, for length of a curve is 1 plus f prime squared. So that means this part of the formula in blue right here, the f prime squared, has to be this part, right? Because all the rest of it is there. The square root, the 1 plus, it's all there, right? So what that tells me is f prime's got to be what? Or f prime squared's got to be x. So what's f prime got to be? Square root of x, which is what Richard said, right? But that's f prime, not f. Right? How do we get f? Antiderivative. So we have to raise that up to the 3/2, divide by 3/2. So our y is actually the function 2/3 x to the 3/2. Now there could be a plus c on there, but that just shifted up and down, and that's not going to change the length of the curve. Okay? Now if you graph that, they didn't say you had to graph it, but it graphs something kind of like a piece of an x cubic. You wouldn't have any negative x's because you can't put a negative x into a square root, right? That's at the bottom of that is a 2, which means it's a square root. So you couldn't put any negatives in, so it looks something like that. So from 0 to 1, we'd be talking about this piece of curve right here. Okay? So for this function, this piece of curve right here is how long? 1.219. Okay? So that was a whole thing that we ended up the class period on Friday with, was that you've got an integral here. It just is a number. A number can mean a variety of things, right? What we said, like if the number 8, or whatever number we use for, I don't remember. 6, right? 6, what's that mean? Number of weeks till you graduate, you know, how many dollars you have in your pocket, you know, whatever. Score you hope to get on the AP test. You know what I mean? It's just a number. It can mean a variety of things. This is just a number, 1.219, it's just a number. And one way of thinking about that number is it's the area under this curve. It's that piece of area, 1.219. Another way to think of it is the length of a piece of this curve from 0 to 1, 1.219, okay, according to that formula we just went. All right, what was the next one that we had? 39 was, what'd you get for 39? Anybody?
1.571.
Pi half. That's actually pi half. Pi half. Okay, and what was the next one?
43.
And
27.
I had
7.634 round. 7. Okay, we got some issues with that one. What's the difficulty? What was the function on 43? X to the 3 halves. So we want the length of that curve. That's close to what we just got to do. From where to where? From 1 to 4. So it's going to be the integral from 1 to 4, square root 1 plus. I mean, I didn't plan to spend too much time on it because there really isn't anything to this, is there? Just typing it in right. All we need is f prime right there. What's f prime? 3 halves. I mean, that's it right there. That's all you got to do. That's 43, right? So I don't know. Somewhere you typed in something wrong or forgot the square. Or, I don't know. So try it again, but it should be 7.634. Okay. So length of a piece of curve. You just plug it into that formula. It's just something you're going to have to memorize. All right, let's move to the. I did? Yes, I did. Number 9. Yes, thank you. Number 9 was talking about this integral from 0 to 3 of 5t squared minus, what is it, 20t plus 50 dt, and I'm guessing some of you probably typed that in your calculator. You did it. What is it as an answer? Yeah, I don't think you had to, but I think you probably did. So 105. Now, that 105 has no meaning to it other than it's just a number. It's just the value of that definite integral. But now let's attach some meaning to it. So, in part A, we're going to say that the function here, here's the function, and then of course we got the dt, and I want you to keep thinking about these as units. They tell us that this is going to be miles per hour, and this is going to be hours, and they told us this was speed, not velocity. Now, why is that important? Speed's always positive, which means we're going in one direction. We're just going in one direction, so we don't have to worry about net distance traveled. Now, I wrote something up here on the board that's important. It's going to come important, especially in part C. When we talk about the integral of a rate of change, which is what we have here, the answer to that is the accumulated net change. We only get total amount of change if what? If it's the absolute value, or we know that the rate of change is always negative. As long as it's in one direction, if the rate of change is in one direction, then we know that the net is the same as the total. But otherwise, or we put the absolute value bars in. But otherwise, if we just do the integral of a rate of change, it's the net. I suppose I should write that there. It's the net accumulated change. Now, why do I say that? Well, because when we're doing distance, we don't use those words usually. We use net, but we don't use the word accumulated or change. So if this is miles per hour and this is hours, what do you get when you do the interval? What's the 105? Miles. But now we got to be better than that. If you were answering question 9A, you'd have to be more specific than saying 105 miles. Total distance traveled, keep going, from midnight to 3 a.m. From midnight to 3 a.m., we went a net, which is the same in this case, in this problem as total, distance traveled, and I would say in both, net distance and total distance, I would put them both in there probably, of 105 miles. Now, what we could say is our total change in miles was 105. Think about that. If you started at 30 and you went to 135, right? That's your net accumulated miles, right? Or change in miles. You went from 30 miles to 135 miles. That's a change of 105 miles. Now, we don't really say a change of 105 miles. We say distance traveled. We say we traveled 105 miles. Okay? So you go to part B, and it's pretty much the same thing. They just tell you it's what, feet per second? And then the dt would be in seconds. So this is 105 feet. That'd be the same thing from midnight to 3 a.m. Okay, now here's where it starts getting tricky. And here's where, you know, on our next quiz, if I want to put something in here like this about interpreting these things, you know, to make it a little more challenging, I would put something like part C. They say it's acceleration. What are the units? Feet per minute squared, feet per minute. And then, of course, the dt would be minutes. What's the 105 now? Now, how do you say that and have it make sense? From midnight to 3 a.m. No, it would be 3 a.m. It'd be, is it? It wouldn't be 3 a.m. It'd be 12 to 12:03, right? It'd be because we're doing minutes. So from 12 midnight to 12:03, or for the first 3 minutes after midnight, what?
The average would change.
No, the word average wouldn't be in there.
Total?
Or net. Is it net or total? Do we know that this acceleration is always positive? We don't know that, right? They didn't tell us. Now, I think it might be. I think this function, if you graph it from 0 to 3, actually is always positive. But let's say we didn't know it was always positive, okay? So we better use the word net then. Okay, this integral, remember, this integral always gives net. Unless you know that it's always positive or always negative, then it's going to be net and total be the same. Okay? Total's only if you do the absolute value. Okay? Okay, so it's the net what?
Velocity.
It's not the net, that doesn't quite tell. You got to get the word change in there. Okay? See, we didn't have to here. I said it's a net change in miles because that means we were at 30 miles, right? If let's say that's what it was at 0. And then at 3, we're at 135 miles. So we went from 30 miles to 135 miles. The change in miles was 105. That means we traveled 105. So we could say the net distance traveled, okay? But it's really a change in miles. This is a change in velocity. So what's that mean?
You started off at 0 feet per minute at some point, you reached 105 feet per minute.
Well, not at some point, at the 3 minutes. Or I could have started at 30 feet per minute and ended up at 135 feet per minute, right? I had a change of 105 feet per minute. Now, if it's positive, that would mean a gain, right? Doesn't that make sense? Think of the chart. If acceleration is positive, it means velocity was increasing. So it means my velocity increased. Since it's a positive change, that'd be an increase of 105 feet per minute. But it's not average velocity is 105 feet per minute. It's not that the velocity is 105 feet per minute, right? It's that, so to say net velocity is 105 feet per minute isn't right. The velocity is not 105. What it is, it's a net change in velocity. See? So we got to get the word change in there. So we're talking rate of change here. We do the integral of that. It's accumulated change. So the one we focus a lot on is going from velocity to distance. And we've probably fooled ourselves into using some terminology here that's probably not that accurate. It works with distance, but it doesn't work with other rates. Okay? So the way to say that is the net change in velocity is 105 feet per minute. Okay, which in this case we gained 105. We're going 30 feet per minute, now we're going 135, or whatever the case may be. Or like Steve said, we went from 0 to 105 or whatever. Okay, that's important. That's really important. It's going to come in the free response questions in our test review stuff quite a bit. All right, let's move to that motion packet, and I want to go to this page right here, the worksheet 2 page. This is the older one, not the one where we did the fill in the blank. This is the older motion worksheet packet. So the rest of today is going to be, now focused on some review stuff. Okay, review stuff. So we're going to do that today. We got our lemon slicing lab tomorrow. Terry was going to be gone tomorrow for something else. Oh, soccer. Oh, you know what? I bet you won't miss. Because the way the weather's looking, you probably won't. So that actually worked out. So hopefully Terry's better. So we're going to do some review stuff. Tomorrow we'll do this lemon slicing lab, which is new stuff. It's stuff leading us to section 7.2. We'll work on that for several days. Probably do some review stuff. Probably might start another packet. I don't know. We'll wait and see. Or some review stuff Thursday, and then maybe come back with some more new stuff on Friday. We'll kind of see how things go. If the track meet gets moved to Friday, I have no idea. But my guess is looking at the weather Thursday, it doesn't look horrible right now.
Tuesday night we're supposed to get some.
But we're supposed to get some snow Tuesday night a little bit. Wednesday doesn't look very nice. Thursday looks a little better. Friday looks a little better yet. So it's possible the Omaha meet, which would affect some of you, might get moved from Thursday to Friday. So if that happens, then we may alternate some things in there, whatever. So we'll kind of play that by ear. But anyway, so look, we got some review stuff to do today. All right. Let's see. We never did talk about number 4 down here on the front of this one. I don't think, did we? Well, it's not on the front, I guess, but it's this page right here, worksheet 2, sample problems. Okay, it's actually the back side of the first page. Number 4, is there guaranteed a time since its acceleration is 0? Justify your answer. This is a velocity. They say, is there a time guaranteed that the acceleration is 0? What did you say? Yes. Hanley, what did you say? Yes. So if we have on a chart velocity and acceleration, and she is telling me that the velocity is accelerating, this is velocity, excuse me, not accelerating, increasing. The velocity is increasing all the way. Now, this is an important word right here. This velocity function is differentiable, which means what? Derivative exists everywhere, slope exists everywhere. Is the function defined here? Is it continuous?
Yes.
If it's differentiable, it's also continuous, right? So there's no holes or gaps or jumps or anything. So we know there's a nice smooth curve. Okay. So we know that if the velocity is increasing, the acceleration has to be positive. And then the velocity starts to decrease here after 8. So we know that the acceleration is negative. So the acceleration is positive, then has to go to negative. Doesn't at some point it have to be 0? And what theorem is it that said that? That'd be a great justification. Not the mean value theorem. No. Oh, okay. Well, that's closer. No, it's one of those 3 theorems we have. Holy cow, boy. But there have been times where you guys kind of put the other class to shame, but boy, they got you on this one. I tell you that, guarantee it. Maybe just one person, the rest of them had no clue. No, what's that theorem? If acceleration is positive, there you go. If the acceleration's positive, and then after 8 it's negative, and somewhere it had to cross because it has to hit all those points. Yes, say it loud. Okay, I heard mean value theorem. That's the only one I heard. Yes, intermediate value. Well, no wonder everybody heard you say that. I said no. Well, intermediate value theorem is what says that. Okay, since and plus the stuff from the chart. So you'd say something like since the velocity is increasing until 8 and then decreasing after 8. That means the acceleration would be positive before 8 and then negative after 8. And so therefore, since it's differentiable, meaning it hits all. Now, an intermediate value theorem, it only had to be continuous. It didn't have to be differentiable. It said to be continuous. It means it's going to hit all the points in between. So the acceleration would have to be 0 at some point. Okay, let's go to the next problem. And now you have this thing. You got a sharp point in there. This is a velocity graph. Okay, is the particle moving right or left? Well, that's when the velocity is positive, it's going right, negative going left. So I'm going to spend a lot of time on this. When's it moving left? Again, that's when the velocity is negative. Acceleration, that'd be what? For this graph, this is velocity. Acceleration's a slope, right? So whenever this graph's going up or going down, that's when the acceleration will be positive or negative. Average acceleration, okay, now let's talk about these last two. Average acceleration, there's 2 ways to do this one. And it's kind of cool seeing how they're basically the same thing. What's one way to do this one? Come on, there's 2 ways, so surely you got one. Did it use an integral?
Nope.
Okay. Did it do
4 or 5?
4?
Nope.
Oh yeah, you're
Well,
thinking of
5
5.
doesn't either.
You're thinking of the theorem. Let me see what you got.
Well, now you're going to be judging me for being wrong.
No, that's good. Now tell me where you got that. Tell me where you got those numbers.
The graph?
Where'd you get? Tell me the first number you had on top. Yeah.
9.
Isn't that v of
2.
v of 2?
Yeah,
Okay, that's fine. It doesn't matter what order we subtract. And then v of 4 over, right. That's slope between 2 points, isn't it? That's just change in velocity. Now, why would that be the case? Well, this is average. Now, we said when you hear the word average, there's 2 ways you can think of it. Average rate of change, average value of a function. Those are 2 different things, but they're actually very closely connected. Average rate of change is like slope. Slope between 2 points. Well, what's the slope of, if you want average acceleration, that's like saying the slope of, acceleration is the slope of velocity, right? Acceleration is the slope of velocity. So average acceleration is like saying find the average rate of change of velocity. Find the average slope of velocity, which is slope between 2 points. So we just take our velocity curve and we do the slope between 2 and 4. And sure enough, that gives you negative 3 over 2, negative 1.5. Now it said units of measure, so what was it in this problem? Feet per second. Wait a minute. Yes, it would be. You're right. Because velocity up here is feet per second, and this is seconds down here. So that's feet per second divided by seconds. So feet per second per second. Okay, that's one way to do it, and that's a good way. Now there's another way we heard, we've used the word average. The average value of a function. What is that formula? The average value of a function. It's the integral from a to b, f of x, dx, over b minus a. That's the average value of a function. What function are we trying to find the average of here? Acceleration. So in this example, we're doing the integral from 2 to 4 of the acceleration function over 4 minus 2. Now, how do we do the average, or how do we do the integral of acceleration? Well, fundamental theorem part 2, we do what? Antiderivative. What's the antiderivative of acceleration? Velocity. So we plug in a 4, we plug in a 2, look what you get. Same thing. Same thing, right? When you're doing average value of acceleration, because it's antiderivative, you do that. Or you think of it as an average slope of velocity, it's the same thing. So they're really connected. They're really connected, all right, as far as what they end up being. But either way, we get -3/2. So either way you thought of that is good, and I hope you can see both of them, all right? I hope you can see both of them. And then is it guaranteed that V prime would equal -3/2, which is what we just found up here?
Yes,
Why?
because it had to cross the mean value.
The mean value theorem says that the slope between the endpoints, there's got to be some point that will equal that. Ryan?
That's only if it's differentiable.
Mean value theorem only applies if the function's differentiable. If the function's differentiable, then whatever the slope between the endpoints is guaranteed to hit that slope somewhere. But differentiable means no sharp points. So if are we guaranteed for V prime to equal -3/2? That'd only be if V of 4 minus V of 2, so if the slope between the endpoints of the velocity curve, which we just found to equal -3/2, if the function's differentiable, we'd be guaranteed that V prime somewhere would equal -3/2. It's not differentiable, there's a sharp point, so we are not guaranteed that. And so the answer to that is no. Okay? So these are really good. I'm really trying to, these problems I'm giving you in these various packets, and the same thing we're going to have today, are, they just tie together a lot of the different things we've learned and put them in some problems with some units and some meaning. Okay, and then the last one, we'll just run through very quickly, but then there is a part of it I want to do. So this is a position function. So when's it moving to the right? What are you going to do? When it's moving to the right or left, you're going to do the velocity, and you're going to plug in a 0, right? So you're going to do the derivative, and they want to know at 0, is it moving right or left? So you're going to do the derivative, you're going to plug in a 0, okay? At 1, is the particle velocity increasing or decreasing? Yeah, velocity increasing or decreasing, you need to find out if the acceleration is positive or negative, and that's the second derivative. Now, you have said equals 0, because they just want to know at 1. If they wanted to know when is it increasing or decreasing, then you'd have said equal to 0 and find your points, do a number line. But they just say at 1. So do the second derivative, stick in a 1. If it's positive, the velocity is increasing. If acceleration is negative, okay? Fine. Oh, now here's where you have to do it. All values of t where it's moving to the left. So what do you do there? First derivative, set equals 0, do number line. Okay? See where it's moving to the left. Now, what do you end up with? What are the points on the number line? 1 and 3. Positive, negative, positive. So it's moving to the left from 1 to 3. From 1 to 3. All right, now, I want to talk about number 4 here. And again, I want to do it 2 different ways. And it's very critical that you see both ways. Did you use calculators on this problem? If I don't tell you not to, you're using them, aren't you? All right. So if you're using a calculator on this one, what would be the fastest, easiest way to get total distance traveled? Integral, absolute value of, no, it better be of x prime, isn't it? Not x. It wouldn't be the integral of x. It'd be the integral of x prime. It's got to be the absolute value of velocity. It's got to be the absolute value of velocity. So the fastest, with a calculator, the fastest, quickest way to get total distance traveled is integral 0 to 5, what was it, 3t squared minus 12t plus 9. That would be the fastest way to go. And the answer was 28. Now, I'm going to throw a wrench into this. This would never, with an easy function like that, ever be a calculator problem. This would be a no calculator problem. Okay? So let's do it. Why would that make it harder without a calculator? You can't just do that integral now, right? You got to split it up. Remember the problem we talked about earlier? And where do you split it? At the turnaround points, right? This particle is moving back and forth, and we want the total distance traveled. We got to know how far to go from here to here, and then from there to there, and then from there to there, and then from there to there, right? We got to find those points. So we got to find all those points. So here's what this would look like. Now, we've already done a bunch of the work up above. We already did x prime and set it equal to 0, and we got what? 1 and 3. And we already know it's going to the right, then going to the left, then go back to the right. How can we use this information now to find how far it's traveled? But we put it where? What do we do with 0 to 1? Make a table of values of what function? It's got to be the position function, right? So it's actually, you say table of values, I think it's like a list of candidates. Isn't it really? Think about when we're doing absolute max. What do? We want a list of candidates for the x function. We do the derivative, set equals 0. And what are our candidates? Where the derivative is 0, which would be 1 and 3. Where it's undefined, which aren't any. And the endpoints, which would be 0 and 5. But it's kind of like doing a list of candidates. Now, what does x of 0 tell? So put a 0 into that original x function. Get your calculator ready here and put those in. Put 0, you get 11. That isn't easy. Now, what's that tell us? That's where this particle started. On the x-axis at time 0, it was out here to the left. Okay? All right. Now what would I put in next? I'd put in a 1. Because what happens at 1? Turns around. So let's see where it turns around. Okay, so put in a 1. What do you get? 15? This is how you would have to do this one if you weren't using a calculator. Now, could you have somehow graphed this parabola by hand and saw where it crossed and blah, blah, blah? I mean, yeah. Matter of fact, in my day, before we had the fancy calculators that would solve and do absolute value and an integral, whatever, we did some of that. We did some graphing of absolute value, but I think what we learned after doing some of those is this is a lot easier. Just this list of candidates thing. So we just did it this way. Okay, so now what would I do? Now let's see the next time it turns around. Where is it? Oh, it's back at 11. So it was at 11, then it went to 15. Now it's back at 11. Net distance traveled right now is 0, but its total so far is 8, right? 4, then came back 4. All right, now what? Now we put x of 5. Where is it now at the end? It's at 31. So how far to go there? 20. So it went from 11. So it went from 11 to 15, back to 11. So it's traveled 8 so far. And then it went 20 more. So that's a total of 28, which of course we knew right here. So we could take that information and get our total distance traveled. Net distance traveled is what? If we had just done 0 to 5 of x prime without bars around it, we'd have got 20, wouldn't we? Because the net distance, it started at 11, ended at 31, so the net change was 20. Net change was 20. Because it was not going the same direction on it. Total change was 28. Okay? So, again, important, this problem like this, always, sometimes in the multiple choice, also in the free response, sometimes with a calculator, sometimes without. But always is in there somehow. So you've got to be able to do that. So our focus today is going to be on what the stuff we work on is going to be on this chart. This is kind of a chart problem, basically. Do the derivative set equals 0, find the turnaround points, that kind of thing. All right. So we want to do that. All right. So that was it for that. So go ahead and put that aside. All right. One last thing to do. And here you just might want to do this in your notes somewhere. We're going to work on this problem right here. We want to try to take about 15 minutes, 10 to 15 minutes for this, and then give you some work time. All right. This has to do with differential equations, which is another major topic that's always in the free response. It's one of the ones we don't always do as well on, and so I want to try to do some more of these as we go into the next several weeks. And a couple of the new things we have to do in Chapter 7 involve differential equations, so we'll be ending up with some of those things as well. Okay, everybody understand what's happening here? They block the river so it's dry so they can build the dam. As they're building the dam, even though the river's blocked, the groundwater is seeping through and starting to collect and rise up behind there. As they build the dam, they're getting some water behind there. And at the time they finish the dam, the water's 30 feet high behind the dam, and then they unblock the river, and of course it all fills up then. And this differential equation models how fast the water rises after they unblock the river. Okay, this is how fast the water rises behind the dam. That's a differential equation. Now, quick review. We had 3 different types of differential equations. What was the first type? Ones we know how to solve. Is this one of those? Can we just do the antiderivative of that thing right there? This is h prime. No. Not do the antiderivative of this one. Why not? It has h. What does it need to have in it if we can do the antiderivative? T or x has to be our input variable. We can tell right here our input variable is t. We cannot just do a straight antiderivative of this. Okay, so the second type we had was what? We memorized. And there were 2 of them. What was one of them? Well, AE to the KT was the solution. What was the differential equation? Y prime equals KY. Does this look like that? No. What was the other one? No, there's another one we memorized. There were 2 of them. Had to do with hot coffee. Newton's law of cooling, which was Y prime equals. Okay, we actually had 4 types of differential equations. Ones we knew how to solve, ones we memorized, ones we were supposed to memorize and forgot. Okay, and then the 4th kind. All right, this is y prime equals k times y minus capital T, where capital T was just some constant, the room temperature. Is this one that one? I think it is, isn't it? There's the h right there, the 1/12 is a k. Here's the h right here, the output variable. And then here's this constant, the 10. Okay, I believe it is. Now the solution to that, we won't need it till later in this problem, was y equals t plus AE to the KT. Okay, that's the solution of it. So in our problem, the h equals, right, and we can plug those in. We'll get to that part in a second. All right, so how many people signed up to take the AP test? Might not be too late to get a refund. I don't know. All right. No, that's it. All right. Now, let's do part A. Use the line tangent to the graph of big H at t equals 0 to approximate the height of the water behind the dam after 1.5 months. Use the line tangent to the graph of H. Now, do we know what the graph of H looks like? We have no idea, okay? So let's say, but what is the graph of H doing? For sure, isn't it going up? Because it's the height of the water. So let's say it's going up like that. I have no idea, but let's say it is, okay? Do we know an initial condition on H, by the way?
Yes.
We use that for my x-axis. Yeah, that is an initial condition, isn't it? H of 0 equals 30. Right? We know at time 0, which is right when they unblock the river, the water's 30 feet high. So the H graph's actually going to start up here and then, whatever, be curved like so. Okay, now, at 1.5 months, and they tell us T is measured in months here, okay? So at 1.5 months, like right over here, They want me to use the tangent line at t equals 0. So that would be this blue line here. Right? They would like me to use this blue tangent line. And let's say this is 1.5 right here. Now I'd like to know the height of the water at 1.5, but they're going to tell me to use the tangent line to approximate that. Why would that be an okay thing to do? Well, no. No, not so much maximum. What could I do this? What they're telling me, could I do the tangent line at t equals 0 to approximate the height at, say, 24 months? Why can I do it to approximate at 1.5 months, but I can't do it for like 24 months? Because 1.5 months is pretty close to 0. And, okay, again, we did this not too many class days ago. Might have been weeks ago, but it wasn't very many class days ago. As we talked about linear approximation, a tangent line to a curve, the points on the line are pretty much the same as the ones on the curve as long as you stay right around the point of tangency, right? So 1.5 is not too far away, so this y value on the h graph, which would be the height of the water, is not too far off from this point on this line. Now we can't find the point on the h graph because we don't know what the h graph looks like, right? We don't know. I mean, could we do the solution over there? Yeah, but forget that for a second. So what do I need to find here to do this then? To find this point right here.
Put it into the TH.
No, no. What do I do to find that point right there? Say it loud. Got to find the equation of tangent line. This is a tangent line problem. Got to find the equation of tangent line. How do you find the equation of tangent line? Slope and a point. There's my point. What do I need?
Slope.
I need the slope. I need h prime is 0. Do I have the derivative of h?
Yeah.
Yeah, that's a differential equation. I got it. So all I have to do is plug in a 0, right? No, don't go over there. Stay with this. I want to know h prime at 0. So what do I plug right there? No, forget that over there. What am I going to plug in right there? 30. 30, right? Because at time 0, what is h? 30. At time 0, h has a value of 30. So I want to find the slope at time 0. I got to plug a 30 right there for h. Okay? All right. So 30 minus 10, 20 times 12. This would be a no calculator, by the way. 20 twelfths, which we reduce to 5/3. Right? So that's 5/3. So how do I write my line? 5/3 plus 30. So I get y equals 5/3 x plus 30. There's my tangent line. Now what? Trying to find this point right here. Now I should have used t here instead of x actually, but plug in 1.5. So I get y equals 5/3. I should have put h actually. H. 5/3 times, I would put 3/2. That's a good move. There's no calculator. What's 5/3 times 3/2? 5/2, which is 2.5 plus 30. So at 1.5 months, 32.5 feet of water. Now, is that the exact answer? No. That's the point on the curve, on the tangent line. But since 1.5 months is pretty close to 0 months, we think that the tangent line is a decent approximation of the actual curve. Okay, very common problem in a differential equation is have you do this tangent line approximation. Why? Because you need a point and a slope. Well, usually in the differential equation problem, you have an initial condition. So there's your point. And you got your slope because they give you the differential equation. So you got the derivative. So your information's all there. Tangent line is very easy to do. Okay? So you don't know what h is, but you can estimate it with the tangent line. So very common type of problem. Okay? All right. Next question. Now, I'm going to actually skip ahead on this one and look at the question before I read the first part of it. Is our answer in part A, which was that dot on the blue line, was that an overestimate or an underestimate? Now, in my little picture, it was what? In my little picture, it was an overestimate because I drew my H-graph like this. Do I know that's how the H-graph was? So what was it that caused that to be an overestimate? Why was the line above the curve? Because the curve was concave down. Did it have to be concave down? No. So what's going to determine whether my answer in part A was an over or underestimate? The concavity, which we find with H double prime. Aha, that's why they told me in this problem, because that's what this is right here, is H double prime, right? So here we go. H prime is 1/12 H minus 10. Now let's do the derivative of that to get H double prime. Now we're doing it with respect to T. So what do you want to distribute that, or what do you want to do the derivative? You want to distribute it? Okay, let's do it. So 1/12 H minus 12/10, what's that, 6/5? Okay, so there's my H prime. Now let's do the derivative of that. What's the derivative? Oh, 5/6. 5/6. Okay, what's the derivative of 1/12 H? Ah, nicely done. You redeemed yourselves because the other class took forever to get that. They were all saying 1/12. Isn't that, why do we have to do an H prime then? It's with respect to T, right? It's the output variable. So we have to tack on an H prime. That's right. What about the 6/5, 5/6? That goes away. So here is H double prime, but they said to do it in terms of H. So we have to take and plug H prime in right there. So H double prime is 1/12 times 1/12 H minus 10. Or I could have used the other one, I guess. Well, this would just be 1/144 times H minus 10. Right? There you go. Again, so far, all this could have been done without a calculator. So we got, that is H double prime. Now, how do we tell if it's concave up or concave down? Remember, this is at 1.5. If it's positive or negative there. Now, what was the... Actually, we want to know if it's concave, if it was concave down or concave up at T equals 0, actually. Because that's where our tangent line was. So we need to know if it was concave up or concave down there. Actually, it probably wouldn't matter. We could do either one. But because what do we have to plug in right here? We have to put the output, right? We have to put H. And so we had the output of 1.5. I think we could do either one. It would be fine. But what if we put in 0? Well, we don't put in 0. We put in 30, right? So if we put in 30 here, 30 minus 10 is 20. 20 over 144. Well, but it's positive. That's all we cared about, right? Is it positive? All right? It's positive. Now, if we'd have wanted to do a 1.5, we could have plugged the 32.5 there, right? That's not technically H. That was on the line, but we could have gotten it. So we're getting a positive number. So when we put in our 30 here, H double prime is positive, so therefore it's concave up. So my picture was incorrect, right? So our answer was actually an underestimate. An underestimate. Okay? And of course, and it says use a second derivative to determine that. You'd have to justify that answer. Okay, and finally, find the particular solution with the initial condition. So now here's where we go to our memorizing. Now, one of the new things we're going to learn is we'll actually learn how to solve this one, Newton's law of Coulomb. But for right now, we'll just go with our memorized version over here. So the solution is the original function, so that's H equals what? Come on. No. This is it right here. What's big T? 10 plus, what's A? It's A. E to the 112 T, right? K is this number in front. K is the number in front, which is 112. T is the 10. A, we don't know. How do we find A? Solve for what? Put in our initial condition, right? We've got to put in our initial condition. That's how you find the constant, the unknown constant differential equation, right? It's an initial value problem. Initial condition plus the differential equation. So here's our solution. So we put in a 30 for H. We put in a 0 in for T. So e to the 0 is 1. A would equal 20. So our particular solution would be 10 plus 20 e to the 112 t. Now, what's the height of the water then after 2 years? No. Put in 24 for t because t was in months, right? Of course, we can see why there was a 1/12 there now. 1/12 times 24 is 2. That's why there's a 1/12 because it was months, not years. So H is 10 plus 20 e to the second. Now, we said this was no calculator, so if there's no calculator, you have to stop right there, right? If it was a calculator, you could go ahead and plug it in and see what that decimal is. Like 100, they did 150 something or whatever feet after 2 years. Okay, that is some of the basics of a differential equation problem. All right, your homework is these are just a series of problems that are like free response problems. They're multiple part, just like the one we just did there, just like that motion packet, where they give you some information and then they ask you questions about it. Okay? Now, make a note here at the top of each of these pages. The first page would be a no calculator. Most of these out of this packet that I give you here, they're called step-by-step problems. Most of these, if they don't say calculator aloud, they mean it to be no calculator. Now, 30, I'm going to say you could use your calculator there, but I'm also going to talk about how it could be no calculator. Okay? With the Angry Bird
Yeah.
logo. Number 31 is no calculator. Okay, 32 and 33 would be calculator. Now, I haven't really worked through 32 lately, and so why that one would be written as a no calculator, I'm not quite sure. But I'll let you do calculator 32, and then 33, of course, it does say calculator. Okay? Now, for tomorrow, I want to have 29, 30, and 31 done. 29, 30, and 31. So you can go ahead and get started.